Hello, and welcome to my Honors Capstone project presentation. My name is Alec Brandell, and I'm a senior in the Engineering Honors Program studying mechanical engineering. For my capstone project, I analyzed various data signals from wind turbines in an attempt to classify long-term wind turbine health and performance. This project was sponsored by Invenergy and advised by Professor Wooldridge. Here's an agenda of what I'm going to be covering today. First, I'm going to provide a little background, then discuss the motivation of my project and the specific goals. Then I will cover some benchmarking and existing solutions, and then dive into my analysis and the results of the analysis. Lastly, I will discuss some of the lessons I learned in this project and the recommended next steps. So first, a little background about wind energy. Wind energy is a renewable energy source that converts energy in the wind to electricity. With the growing threat of climate change, wind energy has proven to be an excellent solution to decarbonizing the electricity sector due to its scalability. Wind turbines are able to be deployed at large scales and are therefore able to meet high energy demands. As a result of this, wind capacity continues to grow in the US and throughout the world at a rapid pace, with the current wind energy capacity in the US being approximately 118 gigawatts and the global capacity being approximately 744 gigawatts. In the US, wind energy makes up about a quarter of all renewable energy capacity. So with an increased capacity comes an increased need to further understand and quantify the long-term turbine health and performance. Therefore, the goal of this project was to design a system that compiles subsystem performance metrics into an overall turbine health score. This would allow for a more holistic understanding of performance at both the turbine and site level across multiple time periods. Additionally, so this project can be built upon later on, this score should be dynamic and modifiable to add more subsystems when needed. There are already a few metrics for quantifying wind turbine health and performance, the first of which is deviation from the power curve. The power curve is a plot of rated power versus wind speed, and this curve varies based on turbine type. Comparing the measured power curve to the rated power curve is a popular way to detect underperformance. The second is mean time to failure and mean time to repair. These are essentially a study of how long it takes for a turbine or a subcomponent to fail or need repair. This can be compared to turbine lifetime to determine how much longer a turbine is expected to last, or when the next maintenance event may be needed. The third is turbine reliability, which is a look at the number of failures per year for each individual turbine. And the last metric is gearbox and drivetrain health, which involves studying oil debris, vibrations, and gearbox temperature to detect issues with the gearbox systems. This can then be extrapolated to overall turbine health. So in the benchmarking process, I also looked into which signals could potentially be included in this project. A really good starting point was the SCADA system monitoring variables, where SCADA stands for Supervisory Control and Data Acquisition. Essentially, this flowchart shows the different data collected from wind turbines and their subcomponents. After discussing these various signals with my mentor at Invenergy, these signals boxed in red were prioritized for this analysis and then ranked based on priority. So with the data signals selected, the next step was to start analyzing data. I used Python to conduct all of the following analyses because it's very intuitive and it's very helpful in parsing through large data sets. The first step in the analysis was to filter out known offline periods so that I could focus in on the times when turbines are generating energy. The second step then was to compare the measured active power to rated power at the turbine level to get a feel for how a wind turbine is performing when it is performing. The third step was to study the reactive power load distribution across turbines to determine whether or not this distribution is even. Next, I calculated the standard deviation of blade pitch angles for each turbine to determine whether or not the blade pitch system was pitching the angles properly. Next, I analyzed the amount of time each turbine spends in each digital state. Then calculated the tip speed ratio, which is a very common metric used to measure turbine efficiency for each turbine. Then I looked into trends over time and monthly performance for all of these different metrics and plotted each of them versus time and also versus wind speed to analyze and look for trends. I also then considered the duration of offline periods each month. So ultimately, after conducting all of these analyses, I realized that trying to synthesize all of these different studies into one single quantity would cause a lot of understanding and information to be lost. Therefore, the optimal way to display holistic turbine health is through a turbine health dashboard instead of a single turbine health score. This dashboard, in its current state, would display 3 values per turbine. It would display the percent time each year a turbine is available to generate power but is not generating. This is also known as downtime. It would display the ratio of measured active power to the rated active power averaged over the year. And it would display the standard deviation in blade pitch angles averaged over the year. These monthly scores would also then be calculated. So for a turbine, you would also be able to see the distribution of these scores across each month, in addition to seeing the annual average to get an understanding of performance over time. Here's a flowchart that shows the hierarchy of the scores on this dashboard. At the top would be the site level score. So this would essentially be the percent downtime, the active power ratio, and the standard deviation in blade pitch angles averaged across the entire site. These site level scores could then be directly compared to one another to compare health and performance between sites. Underneath the site level score, you would then have the turbine level scores, which could be used to compare health and performance between turbines. At both the site and turbine level, you would then have annual scores and monthly scores to view trends over time. Here's an example of a plot that could be used or included in the dashboard. So this bar chart shows the annual average active power ratio for each turbine across the site. For the sake of confidentiality, the y-axis has been removed and the turbines have been renumbered. It's immediately clear looking at this plot that some turbines are underperforming relative to others. And similar plots could also be made showing the annual and monthly average standard deviation in blade pitch angles and the percent downtime to get a graphical representation of exactly the difference in performance between different turbines. So moving on to the next steps of the project, the percent downtime metric should be modified to show the total amount of energy that could have been generated had the turbine been generating power. This will help greater quantify the magnitude of the losses being experienced. The analysis should also be expanded to include different sites in multiple years so that comparisons can be made between different sites and longer-term trends can be analyzed. Additional data signals like current and voltage should also be included in the analysis for potential inclusion in the dashboard. And lastly, an interface would need to be created for the dashboard so it can actually be used. So there were a lot of lessons that I learned in this project, but I want to focus on 3 for the sake of this presentation. The first was to stay organized. In conducting all of these analyses, it was definitely hard to keep track of everything, especially given this project was completed while still doing a full course load. So it was very easy to lose track of what I was doing, and taking breaks between working on the project made it a little hard to keep track of things that I was doing. So staying organized was definitely something that I learned. The second lesson I learned relates more to the process of finding my capstone project. So I was super fortunate to have gotten to work with both Invenergy and Professor Wooldridge. And without cold emailing them, I wouldn't have had a chance to work with them if I didn't reach out in that way. And the typical saying follows that the worst someone can do is say no. So just don't be afraid to cold email people and ask them to work with you. The final lesson I learned was to be adaptable. Project specifications can change as you get deeper into a project, and that was something that I especially noticed, that as I was analyzing data and discovering new things, I would then find even more things that were worth exploring and looking into that I didn't initially know about. So throughout the project, I had to constantly be adaptable and be ready to shift gears and explore different things as they came up in the analysis. So to finish up this presentation, I would like to thank Professor Wooldridge for being my faculty advisor and providing me with so much great advice regarding data management and technical communication. I would also like to thank the team at Invenergy for sponsoring this project. In particular, I would like to thank Jim Cluse, my mentor at Invenergy, for meeting with me weekly and providing me with so much guidance and support. Thank you so much.